Hello everyone, welcome to part 5 of my hidden Markov model video series. So in this video we are going to talk about Gaussian Emission HMM, which is crucial in order to work with continuous observations. Not only are we going to deal with continuous observations in this video, we're also going to show how to deal with multiple observations per time step. So let's dive in. So first of all, let's see this case. So you have these hidden states, which are late stage Cancer, mid stage Cancer, and early stage Cancer. And you have these observations, which are the different ctDNA level, or you can think of it as tumor level. So 0.5 means higher level, and 0.08 means comparatively lower level. So you can see that the observations that we are making here are actually continuous. Just to recap a few things, these are our states or hidden states, early, mid, and late stage Cancer. And M, which are possible observations, are actually infinite because, we can even observe 0.0889 or 0.1112. So these are continuous numbers, so we cannot really list them up inside a list or a set. Then we have the initial probabilities, which are these for the 3 different hidden states, and this is denoted as pi. And we also have this transition matrix from one state to another. Now, these things I've mentioned in more detail in part 1 of the video series, so make sure to check that out. Now, one thing that is different from the previous videos is what is called the emission probabilities. So emission probabilities was those probabilities which were the probability of observing something given a particular state. Now, obviously, we cannot list those observations, so we cannot just make a table. So instead, in Gaussian HMM, what we do is we actually use mean and variance instead. Let me explain. So suppose we have a normal distribution with some mean and some variance. So if I give you some value and if I tell you what is the probability of getting this value from this normal distribution, you will be able to calculate that. That is the main notion or main hypothesis behind the idea. So let me elaborate this a little bit. For example, we are saying that in early stage, the mean and variance of the ctDNA levels is 0.005 and 0.003. Similarly, for mid stage, the mean and variance of these ctDNA levels are 0.1 and 0.05, and you can understand the rest. So if we can somehow get the mean and variance of the ctDNA levels for the different cancer stages, we can very easily calculate the probability of observation. So suppose we want to calculate the probability of having a ctDNA level of 0.5 given that we are in late stage. So we can use this formula. This is a very common formula. I expect that you already know what normal distribution is. If you don't, feel free to check out some resources on normal distribution. So this is how a normal distribution probability is calculated. This is the formula. So in this formula, this is the variance, and the variance for later stage is what? The variance for later stage is 0.1. You can give 0.1 right here. And the observation is, as I said before, it's 0.5. The ctDNA level is 0.5. So we put 0.5 right here. The variance is, as I said, 0.1. And the mean, what is the mean? The mean at later stage is 0.35. So we put 0.35 here. If we plug in all these values, we get the probability. So you can calculate the probability of any observation. It can be any continuous value given any of the 3 hidden states right here. So I think you get the idea of how the emission probability or the observation probabilities are calculated in the Gaussian HMM. Now there is one assumption here that we are assuming that for each hidden state, we have only one Gaussian model that is generating all the observations. Okay, that is why we have only one mean and one variance for each hidden state. Now we are going to relax this assumption later on in this video, but first let's try to master what happens when we assume that there is only one Gaussian model. So how do we change the forward-backward algorithm? Very simple. You just replace the observation probabilities of these two, of this alpha and beta calculation with the formula that I just showed you, the Gaussian formula. Now, if you don't understand forward-backward algorithm, if you don't understand how alpha and beta are actually coming up, you must visit part 2 of the video series. Because this particular video, I should say, only talk about the modifications required to incorporate the continuous case and to incorporate multiple observations per time step. It doesn't elaborate forward-backward algorithm or any other algorithms because I have mentioned and discussed those in great detail with examples in my previous videos in part 2, part 3, and part 4. So similarly, there is this Viterbi algorithm used to solve the decoding problem. So you can actually just replace this with the formula, with the Gaussian formula. Now again, Viterbi algorithm has been covered in detail in part 3 of my video series. And finally, you have the baum-welch algorithm, which is used for HMM training, which is covered in part 4 of the video series. So in here, there are two steps, by the way, as you know. There is the E step and there is the M step. So there is no change in the E step for the alpha, beta, gamma, and psi variable calculation. Only thing is you need to do these two modifications in alpha and beta calculation. That's it. There is no other modification. But in M step, there is some a big modification. For example, previously in the previous videos, we actually calculated the probability of some observation given a state. But now it is not possible, as I mentioned before, because there are infinite possible continuous observations. So instead, what we need to do is we need to estimate the mean and variance of the observation variables for each hidden state separately. So this is the formula. So for example, if we want to estimate it for state I mean, there can be many states. So let's assume that we are doing it for state I. So we just need to multiply the observation at time step t by the lambda ti. So lambda ti, as I mentioned in part 4, is the probability of staying in state I at time step t, right? So if we sum those things up and multiply by the values and we take the sum denominator, it's like averaging, right? It's like averaging. Normally you would just sum all the OTs and you would just divide by the n, by the number of OT. But obviously there is probability involved, so you need to take the weighted sum and divide by the summation of the weights. Similarly, you can also get the variance. So same logic, same argument, but the only difference is now you need to take the deviation for the square because it is variance. So that's the difference. I mean, there is not much difference. Now, let's talk about another case where we not only have one observation per time step. I mean, so far in all the videos that I covered, we only had one observation per time step. But this time we are assuming that we have two observations. One is the ctDNA level, the T1 level, and the other one is the CEA level. So CEA is a kind of protein biomarker that normally gets elevated when people have later stage cancers. Okay, fine. So how do we modify things now? So first of all, we need to modify the emission probability. So now we cannot have only one mean and one variance per state. So for example, let's talk about the late stage. We are going to have two means, one for the ctDNA and one for the CEA. Now, some people who don't really know the algebra may think that there should be two variances for two variables, but those of you who know algebra, you know that when we have multiple variables involved, we have to calculate the covariance matrix, right? That means the different relationships between the different matrices. So for example, this first value 0.15, it denotes the variance of ctDNA level, but the second variable, it denotes the variance between ctDNA level and CEA level. So basically the interaction between these two variables. Now, here we have two variables, that's why we have 2 into 2 size covariance matrix. But if we had 3 or 4 variables, we would have 3 into 3 or 4 into 4 size covariance matrix. For those of you who don't know about covariance matrix, feel free to check out some resources because it is a quite common concept and you should get many resources. So this is for late stage. We have to do the same thing for mid stage and for the early stage. And we are done. Now, the main question is, how do we calculate the probability of some observation given a particular state? Because here we have two observations. So this formula is actually the same as the Gaussian formula that I showed you before, but the previous formula was only for one variable, and this formula is actually generalized. You can use any number of variables in this formula. Let me actually show you and illustrate the thing that I'm trying to make sense of. So first of all, suppose we are talking about time step 1. So here we have 0.5, 0.3. So we push the vector 0.5, 0.3 right here. And this is late stage, so we push late right here. How many variables do we have here? We have two variables, so d equal to 2. And then this will be our covariance matrix of late stage. So, I mean, we already know OT, which is this one. We also know this covariance matrix, which is this one. And finally, new, we also, I think, understand now that new I should be new late because late is the I. Right? So if we put all these things together and we do matrix multiplications and other things, we are going to get a single value that denotes the probability. So now I think you understand that we can actually get any probability or any observation given a particular hidden state. It doesn't matter whether we have 3 or 4 or 5 observations per time step. So in this particular scenario where we have multiple observations, everything is actually the same as the single observation continuous case, except for one change in baum-welch algorithm covariance matrix update step, because previously we had the variance and we would update the variance in the n step of baum-welch algorithm for HMM training. But this time we are going to replace this variance with the covariance matrix. And obviously we will not do any whole square because we are going to do a vector multiplication. So this will be a column vector and this will be a row vector. So if we multiply column vector with a row vector, we are going to get a matrix, and that matrix will be our covariance matrix. So now the main question, the question that I was ignoring so far, what if we assume the presence of multiple Gaussian models in generating the observations from each hidden state? And the first thing is, why would we even make that assumption? Why would we actually think that multiple Gaussian models are there? So let me explain that first. So let's actually take our cancer example case where we have the 3 stages. So we can assume that there are 2 types of patients coming in our healthcare. One is with and one is without inflammatory conditions. So maybe patients who are actually coming up with inflammatory diseases have overall higher ctDNA and CEA measurements compared to those who don't really have such inflammatory conditions. So even in case of early stage cancer, for such inflammatory diseases, maybe the ctDNA and CEA level are comparatively higher. So obviously, we can imagine that the observations are actually coming from 2 different models. That means they should form 2 different clusters. So we should use 2 different Gaussian models per state here. Let me elaborate what I mean a little bit more. For example, let's think about just one of the hidden states, which is late stage. For late stage, we should have particular mean for model 1, particular covariance matrix for model 1, and we should have this. So this means the contribution of the Gaussian model 1 for a particular observation. Same goes for here. Now understand that pi late 1 and pi late 2, if you sum these 2 things up, they will actually equal to 1. That means they are sort of giving a probabilistic view. So maybe you can say it like this. Maybe for a particular observation, given late stage, 30% contribution comes from this and 70% contribution comes from this model 2. That is what it actually is saying. So, I mean, similar parameters will actually have to be there for early and mid stage as well. Let me actually illustrate this with an example. For example, suppose your ctDNA level is 0.4 and CA level is 0.2, and you are assuming that you are in late stage. So what is the probability of that? So first of all, you will apply the Gaussian formula. I mean, n means the normal distribution formula that I just showed you before for model 1, where you use the mean 1 and covariance matrix 1. You will also do it for model 2, where you use mean 2 and covariance matrix 2. But how will you actually add these 2 things up? You will simply use the weighted sum. The first one will be weighted by pi late 1, and the second one will be weighted by pi late 2. That is the contribution of pi. Now understand that in this example, we are assuming that we have only 2 Gaussian models, but some people may use 3, 4, 5, etc. So what is the general formula? So general formula is quite simple. So this is the exact thing that I did here. Instead, we are just actually putting summation k equal to 1 to k, because k can be anything. It can be 2, 3, 4, 5, etc. Now, the forward-backward algorithm and the Viterbi algorithm are going to use this definition of observation probability given a particular hidden state. That is the basic change in these 2 algorithms. And everything is the same. So what about baum-welch algorithm? Because this is always the thing that makes our life much more difficult. So the first thing is, in the E step, we have to actually estimate one more variable. I mean, previously we would just estimate lambda ti. That means what is the probability of having state I at time step t. But here we are going to calculate that, but we are going to also say that what is the probability of a state I being at time step t, given that it is being generated from mixture model K. Right? So how will we calculate this? Very simple. We have lambda ti, which we can calculate using the typical formulas of lambda ti, which I've covered in detail in part 4. Now, you simply multiply it by the mixture component weight and the actual normal distribution probability of observing OT, given that we have this mean from the model K and covariance matrix from the model K. Now, this is the probability. That is why we have to divide it by the sum. So the sum is summing over all the Gaussian mixture models. So if you have 3 mixture models, you are going to sum 3 such things up in the denominator. So in the n step, obviously you now have 3 things here. One is the pi ik, one is the new ik, and one is the covariance matrix ik for any state I. So you will have to update all of these 3 things per state. Now understand that in MSTEP we also update initial probability, transition probability, those kind of things. But there isn't any change in those. So I'm not talking about those. I'm only talking about the thing where we have to make some changes. So pi ik is very simple. You have to divide lambda t ik by lambda t I for all the and sum for all the time steps. So we just want to know the contribution of model k. Similarly, for new ik, that means the mean, you will have to multiply OT, that means the observations for all the time steps, by the weight, and you have to sum up all the weights. I mean weighted average basically. And same thing goes for the covariance matrix. So it's actually quite simple and intuitive. So this is all about the hidden Markov model series. If you like the series, feel free to subscribe and share the series with your friends and others. And a donation link is there in the description. So your donation can also help us make better videos like this. So thank you very much.